let's integrate 8x squared plus 8x plus 2 all over 4x squared plus 1 quantity squared. I'm going to proceed by using partial fraction decomposition to rewrite the integrand. So I'm just going to think about the integrand over here. And what I notice about the bottom is I have an irreducible quadratic factor, 4x squared plus 1. The only roots to 4x squared plus 1 are complex roots. So I'll have to think about that repeated irreducible quadratic. So I know I'll need one fraction of the form ax plus b all over 4x squared plus 1, and maybe another cx plus d all over 4x squared plus 1 squared. Now I need to find the constants a, b, c, and d. I'll proceed by multiplying both sides by the bottom here. Nicely enough, when I multiply by the bottom here, the bottom just cancels and I just get cx plus d. I need to do a little multiplying here. So I get a 4a x cubed plus 4b x squared plus ax plus b. And still that's cx plus d here, so plus cx plus d. That's the only term with a cube in it. That's the only term with a square in it, and I do end up with two things that have an x to the first. So we'll just rewrite this a little bit. And then b plus d is my constant term. I can equate coefficients and create a system of equations. Kind of nicely, there's no x cubed over here, so 4a has to be equal to 0, which in turn tells me that a is 0. And one thing to keep in mind when dealing with these irreducible quadratic factors, a or b on the top of one of these fractions can in fact be equal to 0. And the system will always tell me if that's the case. 4b has to be equal to 8, the coefficient in front of the x squareds, which in turn tells me that b is 2. A plus c has to be equal to 8 as well, but I already know that a is 0, so c has to be 8. So this system's not turning out to be too challenging to solve, and finally b plus d has to be equal to 2. Well, b was equal to 2, that tells me d had to be 0. Well, I'm ready to rewrite my integrand. The first fraction with an ax plus b on top, well, it turns out only the b really mattered because I have 0 times x. And for this one, d is 0 and c is 8. So I end up with an 8x over 4x squared plus 1 quantity squared. And I'm integrating with respect to x still. So now I'm ready to integrate. I'm going to split this into two different integrals. And I have some work here to find those constants. I'm just going to erase that so I have enough room to continue. And now I have two different integrals. On this one, I've already factored out a constant. And on this next one, I have the benefit of already working this problem out, so I know I can leave that 8 right there. If I factored it out, everything would work out the same way. I just know what's getting ready to happen as a bit of a spoiler. This one I recognize as being in the format of a inverse tangent problem. In my head, I'm really thinking about a substitution where u is equal to 2x, and that would make du equal to 2dx. And so that would just be a 1 over 1 plus u squared du, right? These 2's will cancel when I do everything, and I'll just end up with the arctangent of 2x. And now I need to integrate this part. And instead of just thinking about a substitution, I think I really will do a substitution here. I'm going to let v equal 4x squared plus 1. dv is then equal to 8x dx, which turns this second integral into 1 over u squared du. right? Because my 8x dx is my entire dv. And excuse me, I was using the variable v there, so that should be a v squared and a dv. I'd already used u. I wanted to use a different variable. That's what I get for trying to be fancy. All right, so this is equal to, I still have this arctangent of 2x plus, and if I integrate this, I'll get minus 1 over v, so minus 1 over 4x squared plus 1, and of course plus some arbitrary constant. And there we have it. We have found our antiderivative.